Hi everybody, welcome to the lecture about power line rectifiers, inrush current limiting, NTC thermistor and active power factor correction. The inrush current limiter is an important part of almost any power line rectifier and DC-DC converter. In this lecture, we consider three basic types of inrush current limiter circuit: a fixed resistor, a NTC thermistor, and a fixed resistor with shunt switch. A fixed resistor inrush current limiter. It is the simplest inrush current limiting circuit. However, it suffers from the irresolvable contradiction between high inrush current and high power loss on the resistor. It is typically used in the cheap low-power devices like LED lighting bulbs, small wall outlet adapters, smartphone chargers. An NTC thermistor-based circuit is a very popular type of inrush current limiters. It is used in the most of the desktop and laptop computer power supplies, as well as in the most of the commercial power supplies at the power level up to several hundreds of watts. It suffers from very high thermistor operating temperature and long cooling time after turning off. A fixed resistor with shunt switch is the most efficient and flexible solution. The shunt switch can be a semiconductor or electromechanical device. However, this type of inrush current limiter requires a specific load timing diagram, so it is usually used in the high-power inverters or highly reliable DC-DC converters. It is a relatively complex and expensive solution, but it does not insert any noticeable power loss. Fixed resistor inrush current limiter. Let's run a circuit simulation and examine the results. After connecting to the power line, a significant current jerk is immediately detected. There is very high current jerk right on connecting to the power line. It is inrush current, which is known to be every type of the rectifier's inherent disease. It happens because the initially discharged filter capacitor C1 is instantaneously charged to the line voltage through resistor R1. So, the peak line voltage is instantaneously applied to the resistor R1, as shown on this equation. This resistor restricts the amount of inrush current while introducing power loss during normal operation. The higher the resistor value, the lower the inrush current, but the higher the operational power loss. As a result, the circuit's harmful power loss and inrush current value are incompatible with one another. The minimum recommended value of this resistor is 10 ohms, which restricts inrush current to a reasonable 16 amps at 120 VAC power line voltage. 16 amps is shown here. The lifespan of the filter capacitor may be compromised by the increased inrush current values. The inrush current pulse duration is affected by the filter capacitor value. The pulse time increases with the capacitor value. This inrush current pulse corresponds to 10 microfarad filter capacitor and this to 100 microfarad filter capacitor. It is much longer. The energy stored in the filter capacitor C1 at the peak line voltage is equal to the high energy absorbed by the current limiting resistor R1 during an inrush current pulse, as shown in this equation. It is 1.4 joules in our situation. Not all types of resistors are capable of withstanding that energy without damage. Only the composition resistors, both carbon or ceramic, as well as wire-wound resistors, are usable. Any film resistors cannot operate as an inrush current limiter. Let's consider the simplest but not the best fixed resistor inrush current limiter in detail. The operational power loss on the R1 depends on R1 value and input RMS current as defined by the following equation. The load power is given by this equation. The maximum acceptable power loss is about 5% of the load power. However, the lower the loss, the better. Let's run our simulation model and determine both load power and inrush current limiting resistor power loss. The simulation results are shown here. So, the R1 power loss is 0.426 watts, while the load power is 13 watts. Thus, the inrush current limiting resistor power loss is about 3.3% of the load power, which is acceptable, but could be done better when using a more advanced solution rather than fixed resistor. For the sake of reliability, the inrush current limiting resistor rated power should be at least 3 times higher than its power loss at maximum line voltage. In this case, we can use a small wire-wound leaded or SMD resistor 10 ohm 2 watt. The 2 watt carbon composition resistors are difficult to find, while the wire-wound parts are ready available. This is wire-wound part and this is wire-wound part. Ceramic composition resistors are the best by far, but they are very expensive. How to determine a resistor pulse power withstanding capability if it is not specified in the datasheet? The following datasheet plots show the maximum pulse power over the pulse duration for KNP 200 parts. As we only have one pulse, let's use the upper lines. The 1 millisecond pulse corresponds to 3 kilowatt of pulse power. The maximum allowed pulse energy is a product of these two values, that is 3 joules, while the hour real energy is only 1.4 joules. Voila! The cheapest resistor is good enough. NTC thermistor inrush current limiter. The negative temperature coefficient NTC thermistor is the most popular device used in commercial power supplies as the inrush current limiter. Its resistance is strongly dependent on its body temperature. Here we explore a bridge rectifier with inrush current limiter commonly used in a series of industrial switching power supplies with universal input 100 to 240 VAC and 100 watts of maximum output power. The shown simulation model consists of the bridge rectifier with very popular thermistor CL110 and the model of DC-DC converter. The undervoltage lockout and soft start allows the DC-DC converter to operate only if the rectified voltage exceeds 90 volts and otherwise turns it off. If this voltage is lower than 90 volts, the DC converter is off. In addition, it forces the DC-DC converter to start consuming and supplying power slowly, increasing them from 0 to 100% for 10 to 20 milliseconds to avoid overloading the components. Undervoltage lockout and soft start features will be discussed at future lectures. This is CL110 thermistor. It's a disc with leads. Its parameters: maximum RMS current is 3.2 amps. Cold resistance is 10 ohms at 25 degrees C. Hot resistance at 3.2 amps is 0.19 ohms. Body temperature at rated RMS current 3.2 amps is 175 degrees C. Body diameter is 10 mm and maximum pulsed energy is 4.32 joules. The simulated input current is shown here. The inrush current is 37 amps at 240 VAC and 14 amps at 100 volt AC. Of course, if input voltage is higher, the inrush current is also higher. This is the simulated thermistor body temperature. The red curve corresponds to 100 VAC and the green curve corresponds to 240 VAC. At 100 VAC, the maximum thermistor body temperature is 158 degrees C and only 120 degrees C at 240 VAC of line voltage. As you can see, the thermistor body is very hot. The power factor of this power supply stays between 0.5 and 0.6 regardless of the input voltage. The NTC thermistor is also a device susceptible to pulsed energy. In the datasheet, it usually displays the maximum pulsed energy in joules and/or a maximum filter capacitor value in microfarad for a given line voltage. For the CL110, the maximum filter capacitor rating is 150 microfarad at 240 VAC or 4.32 joules. Exceeding the maximum pulse power energy causes a significant inrush current peak and also possible damage to the device. The NTC thermistor simulation model allows us to get all the necessary electrical and thermal information. It is therefore strongly recommended to all power supply designers. The Aura NTC thermistor simulation model accurately reflects all datasheet parameters: cold resistance, hot resistance, a full rated current, thermal capacity, and cooling timing constant. NTC thermistor runs hot. Its temperature can reach 175 degrees C. For this reason, its body should not touch anything around it. To avoid self-desoldering, do not cut leads too short. Leave at least 1 centimeter and use larger copper pads on the PCB. The inrush current simulation results are shown here at 3 filter capacitor values: 150 microfarad, 300 microfarad, and 600 microfarad. The line voltage is 240 VAC. As you can see, at normal filter capacitor value 150 microfarad, the inrush current doesn't exceed 40 amps, which is normal for 100 watt power supply. If the filter capacitor value is 300 microfarad, which is higher than recommended by datasheet, the inrush current is significantly increased, and maximum of the inrush current reached not on connecting to the power line slightly later. It is not good, because it is abnormal operation of the thermistor. At filter capacitor value 600 microfarad, the inrush current goes so high, over 140 amps. This is definitely abnormal value and may cause the thermistor destruction. Fixed resistor with shunt switch inrush current limiter. This type of inrush current limiter is generally used in higher output AC-DC and DC-DC converters. There are two major advantages of this circuit. Low inrush current, it even can be done lower than operational peak current. It is important for higher power DC-DC converters. Very low power loss, actually near zero. The Aura simulation model is shown in the picture. It includes the bridge rectifier, current limiting resistor R1, relay S1, filter capacitor C1, and 500 watt DC-DC converter. For normal circuit operation, the DC-DC converter is equipped with delay and soft start circuits. Let's run a simulation model and explore the results. On turning on, the relay contacts are open and DC-DC converter is disabled until the filter capacitor C1 is fully charged through resistor R1. After that, the delay and soft start circuit turns relay contacts to the closed state and DC-DC converter starts ramping up its power from 0 up to its normal value as shown in the picture. This is load voltage. This is input current. The line voltage is 240 VAC. This is a delay. Delay is necessary to allow the filter capacitor to be fully charged. Then, after closing the relay contacts, the soft start ramps up the input and output power from 0 to 100% during around 10 milliseconds. The delay time is required for charging the filter capacitor before closing the relay contacts. It depends on the value of the current limiting resistor R1 and the value of the filter capacitor. To avoid unpleasant shocks when contacts closing, this time should be at least 100 times longer than the timing constant R1, C1, R1, C1. As previously explained, the current limiting resistor R1 absorbs a lot of pulsed energy, so choose a suitable one. The maximum inrush current in that circuit type is independent of the normal operational peak current. The higher the R1, the lower the inrush current, but the longer the delay time required. The highly reasonable inrush current value is the normal operating peak current value. The images on the right show the simulation results. With the current limiting resistor value 18 ohms, the maximum inrush current is 19 amps, while the normal operational current is 20 amps. Reducing the inrush current is necessary if the primary energy source has the limited power supply capacity, such as a solar panel. The solar panel usually delivers enough current to the DC-DC converter during its normal operation, but it cannot withstand the short overload caused by the inrush current if it is too high. This pulsed overload can cause the main power source voltage to drop, causing the other equipment powered by this source to malfunction. This is particularly important for the power bus of the spacecraft receiving energy from the solar panel or radioactive isotopic battery. Active power factor correction model performance. The main problem with the simple rectifiers is their low power factor. For instance, the power factor of the previously considered rectifier is only 0.5, which is highly undesired at high power levels. As a result, almost all commercial power supplies above 100 watts of output power are now equipped with an active power factor correction PFC circuit. The active PFC is actually a boost converter with a special control logic. To better understand, we have developed the linear model of active PFC. Though it does not contain a real switching boost converter, it functions as a real switching PFC. It consumes energy from the power line and delivers energy to the DC-DC converter exactly like the real switching PFC. The simplified model is shown in the picture. Our linear model of active PFC accurately reflects the internal structure and performance of classic PFC device UC3854, where the switching boost converter is replaced with equivalent linear power source. The typical output voltage of the active PFC is 380 to 390 volts and is independent of the line voltage at 100 to 240 VAC. The rectifier's input current follows the input voltage waveform, emulating a pure resistive load, resulting in a unity power factor. Let's explore the circuit performance. The inrush current waveform is similar to that of the previous slide, but lower in value due to increased R1. However, the steady-state input current is now sinusoidal. After the delay, the boost converter pushes the output voltage from 340 to 390 volts, and the input current becomes sinusoidal, providing a perfect unity power factor. Thank you for your attention. The next lecture is devoted to magnetic circuits. This is email address for questions. Goodbye.